Hello everyone, welcome to another live presentation. This presentation is a quick recap of the Step 8 Machine Learning course CS Internship program. My name is Maliheh Sefat, and today I discuss supervised natural language processing for sentiment analysis. Sentiment analysis is a natural language processing technique used to identify emotions and opinions in text. Businesses use it to understand customer feedback, and researchers apply it to social media trends, reviews, and public opinion. While traditionally used to classify sentiments as positive, negative, or neutral, advanced models can detect a broader range of emotions such as joy, anger, sadness, and fear. Researchers and healthcare professionals utilize it in mental health diagnostics, where AI-powered sentiment analysis can help assess emotional well-being. And that is what we're going to see today. As usual, for good practice, I collected all the libraries and packages in the first cell. I found a very useful uh, data set related to mental health from here, Kaggle datasets. This dataset is a combination of several other datasets. So we download the dataset and read it with readcsv, make a data frame from it, and I named it MHDF. You notice that we have more than 53,000 rows and only two columns. Those columns are statement and a status. Both of them are strings that render as objects in data frames in pandas. In this view, we only able to see anxiety status, but there are other statuses. When we shuffle the data frame with sample frec1, and of course we need to reset the indices, we can see other statuses as well. So with the value count on the status column, we can see how many rows have each label has how many rows. Normal has been repeated more than 16,000 times. Then there's the depression, suicidal, anxiety, bipolar, stress, and the list of them personality disorder with 1,201 occurrences. With the pie chart of Matplotlib, we are able to display a nice distribution of statuses based on percentages. And you see here that 30% of our data frame is normal, another 30% is depression, 20% belongs to suicidal, and the other 20% is composed of the other four statuses. Preprocessing always starts with investigating null values. With summation on the isNull method, we see that there are 362 statuses without a statement. They lack a statement. I don't believe that they are much help to our machine learning models. So I drop any row that has a missing value with the syntax and get the description of MHDF. When we call the describe on numerical data frames, we are able to see statistical information. When we call the describe on textual data frame, it returns the count of non-null values first, then the count of unique values in each column, and uh, this top is the most frequently occurring value in each column, and frec is how many times the top value appear in the column. Uh, in our case, what do you mean is the most frequent statement with 22 repetitions. It's possible for the same statement to have different status labels. This can lead to confusion in classification and introduce noise into the dataset. So I got curious to know how many statements have conflicting labels. I group the data frame on a statement and ask for the number of unique statuses, n unique, and collect those conflicting rows into the conflicting statement variable, and we see that we have 18 conflicting statements. I only keep those statements that have exactly one unique status with this slicing notation. And getting the shape shows that now we have less than 53,000 samples. Now it's time for cleaning. With the help of regex regular expression library, we can clean our text from any unwanted characters. For example, with these raw expressions, we can remove words that start with at sign. Those are the mention names, and we can remove any URLs and also HTML markups. With this, I removed any single letters such as I and A, and here we found the emoticons, classical emoticons or emojis. Keep them in emoticons. After cleaning the text and lowercasing it, then we replace those emoticons at the end of each text and replace the nose, of course. We don't want a nose. And return the clean text. Okay, with the lock indexing notation, I apply the cleaner to all the statements column. And here, for example, we see the statement number 4 that is very clean and nice. I found a very entertaining or amusing, I don't know how to say, informative data visualization for textual data. It can show trending words in any document, and that is WordCloud. We import the WordCloud and ask it to show us the trending words of each category. But in our case, words such as feel, feeling, people, will, those are the words that are not common in English, but they are common in mental health. I don't want them. I want the words that only is specific to any mental health diagnosis. So I collect those words that have been repeated more than 100 times across all the statements with the help of the counter class. And then we make a customized word cloud generator, exclude those common words, and give the filter text to the generator and ask for word cloud. With this for loop, we ask for word cloud for each statement. Here's the word cloud for normal. Yes, that's very pretty. And the word cloud for depression. And curiously, you may notice there are a lot of body parts and bodily functions in word cloud for anxiety. I don't know why. Colon, reflux, abdomen, things like that. And this is the word cloud for suicidal. Predictably, it has afterlife and bullet, bleed, things like that. And here's the word cloud for stress. It has deadline and assignment. There's assignment and professor, things like that. Okay. Starting machine learning. I assigned the MHDF statements column to the X matrix and status to the Y for targets, and then split those into the train and test portions. Getting the shape of the X train shows that it's a one-dimensional array of more than 42,000 samples. These are only text. up until now. How do we feed text into machine learning models? Machine learning models are basically mathematical formulas. How do we feed text into mathematical formulas? Well, first we break down long strings into basic parts. We call them tokens, and then transform those tokens into vectors of numbers. And those would be our features that we feed into machine learning models. For tokenization, I'm going to use NLTK. The Natural Language Toolkit is a widely used open source Python library for natural language processing tasks. NLTK automatically applies punct algorithm. What is punct algorithm? Punct algorithm includes pre-trained language models for sentence segmentation and word tokenization in English. It also includes rules for handling punctuation in sentences, such as comma or exclamation mark. And then there are abbreviation handling. For example, Dr. Smith wouldn't be split into Dr. Point Smith. And after that, I use stopwords from the NLTK. The term stopwords come from early information retrieval systems because they stop being considered for indexing or uh, processing. Since words like and or the appear frequently but doesn't contribute meaningful context, removing them reduces computational load and improves relevance in search engines and NLP models. Porter stemmer is another thing that we use from an LTK. Porter stemmer is a rule-based algorithm that reduces words to their root forms by removing suffixes. It follows predefined linguistic rules to strip endings like ing, ed, or s, simplifying words for text analysis. For example, talking would be transformed to talk. It doesn't focus on derivational suffixes that significantly change word meaning, such as less, full, meant, ness. Removing less from homeless or full from wonderful would alter the word's semantic meaning, which is why Porter Stemmer leaves them intact. Therefore, we import NLTK, and from NLTK, we import word tokenized stopwords and Porter Stemmer. If we don't have them already, we download punct and stopwords. I defined a simple tokenizer and got the set of English stopwords, instantiate an instance of Porter Stemmer class, and feed the text into word tokenized to get the tokens. Then from those tokens, I filter them to be lowercase and not in the stopwords. And then I stem those filter tokens and get the stem tokens to return. This is an example of a test uh, text, and we feed them into simple tokenizer, and here's what we get. This IE is read that is. It would read that is. Running faster makes you stronger, Mrs. Williams. You see that this IE is handled correctly, and Mrs. also is handled correctly. Faster and stronger remain the same, but running became run, and Makes and Williams lost their S here. Now we apply the simple tokenizer to xtrain and xtest to obtain xtrain tokens and xtest tokens. Getting the head of xtrain tokens shows that each document is now a list of tokens. For vectorization, I use two methods. One is the bag of words. The bag of words model is a simple way to represent text data numerically. It disregards grammar and word order, focusing only on word frequency in a given text. Essentially, it turns the document into a set of unique words and their counts. A Bow vectorizer takes this concept further by transforming text into a vector format. It creates a vocabulary from the dataset and then encodes each document as a vector of word occurrences. You see here we have two documents, this sample exam and another exam. And the collective words are these. The vocabulary is another exam simple and this. For this document, we have another. So this element, the first element gets 1, the next element gets 1, and the rest of them are 0. For this document, we don't have another. So the first element gets 0, and the rest of them are 1. Well, we import a count vectorizer from scikit-learn, make an instance of it, and fit and transform xtrain tokens to get xtrain bow, and transform xtest tokens to get xtest bow. Of course, we need to join those lists because vectorizers only receive strings, not lists. With the get feature names out, we can see the vocabulary of Bow Vectorizer, and I chose this slice. This is from the A section of the vocabulary. We can get the shape. You see that the number of rows are the same as the X-train, but the number of rows in the X-train bow are more than 37,000 features. And this is the representation of the sparse matrix. We got a sparse matrix from vectorizers. It shows the coordinations where there are non-zero values. In those two coordinations of the first row, we have non-zero values 2 and 1, and the rest of the row is 0. And of course, you notice that the values are integers. TF-IDF, term frequency inverse document frequency, is a statistical measure used to evaluate the importance of a word in a document relative to a collection of documents. While downweighting common words, TF-IDF assigns higher weights to words that appear frequently in one document but are rare across the entire dataset, making it great for distinguishing key terms. TF-IDF is similar to what we did in our customized WordCloud, but then we manually excluded the common words. Here, TF-IDF does it automatically by calculating higher scores for special words and lower scores for common words. Special words here are things like afterlife, avoidance, delusion, and common words are feel, want, things like that. So we import the TF-IDF vectorizer from scikit-learn and instantiate an instance of it with n-gram range 1 and 2. Here's what n-gram do. Unigrams split the text into single tokens. Bigrams split the text into pairs of consecutive tokens. And trigram split the text into triplets of consecutive tokens. I chose only one unigram and bigram. So we fit and transform xtrain tokens and xtest tokens with the TF-IDF vectorizer to obtain the xtrain TF-IDF, xtest TF-IDF. Of course, we join the list first. And now we have 4 sets of features to feed into the machine learning models. Get feature names out again can show us some of the vocabulary, and here this part is from the bigrams. You see, it's from the Asia country, Asia, depressed, Asia, and see. And the shape of the TF-IDF matrix is much bigger than the Bow matrix. It's more than 800,000 features, and this is the representation of the sparse matrix. In these coordinations, we have these non-zero scores. They are floats, of course, and the rest of the matrix is 0. So I chose three models. One, logistic regression. Even with very low regularization and even with high maximum iteration and even with solver saga, which is suitable for sparse matrix, logistic regression is difficult to converge. It takes a long time. And then I chose another model to be naive Bayes, multinomial naive Bayes. Of course, we need to instantiate two instances of the models, one for the bow and one for the TF-IDF. And we fit the bow model on the bow features and TF-IDF model on the TF-IDF features. We do this for logistic regression, multinomial naive Bayes, and random forest classifier. We have two instances of random forest classifier for bow and TF-IDF features and fit them on the respective set of features. Now we can do prediction. We can predict the outcome or the label on the X test bow and X test TF-IDF with the respective models for bow and TF-IDF. And we have 6 predictions. Okay, for evaluation, I decided to only ask for accuracy score. We import the accuracy score from scikit-learn matrix and get the accuracy score on all 6 models. And you notice that we got the best score, accuracy score from logistic regression on TF-IDF, even though naive Bayes is quick to converge, but it shows the weakest accuracy score. And I got the classification report on the winner model, only logistic regression on TF-IDF, and you see these are matrix for report precision recall. I explained them in the previous presentation. For visualization, we can do visualization with confusion matrix. And I make a customized confusion matrix and give it the model and predictions. I got the names for the X ticks and Y ticks from classes attribute of the trained model on the logistic regression on TF-IDF. This ending underscore shows that the names have been learned from the model. They only exist after fitting the model. So the names correctly correspond to the results. And here's the confusion matrix. The diagonal is the true predictions, and anything else is false predictions. We, of course, want to have the best predictions, the most true predictions, and we want the rest of them to be zero, but that's not possible. That would be overfitting. So, to end the presentation with a fun experiment, I decided to test our models on text samples, and I tested several famous quotes. For example, if we quote Hamlet here and give it to the cleaner, then simple tokenizer and make vectorizations with bow and TF-IDF and feed them to the models, Naïve Bayes says that Hamlet was probably depressed. Thanks very much for watching my presentation.